So today we're going to go over how to show the transfer of electrons between our metal and our nonmetal that results in an ionic bond, how to determine the chemical formula of an ionic compound, and how to write the name of an ionic compound. Knowing how to communicate about different chemical compounds is incredibly useful to your daily life. It seems a little like it might be a little obscure, but actually you're looking at chemical compounds all the time. Everything in our world is made of chemicals. And sometimes, especially on our food and hair care products or makeup products or skincare or cleaning supplies, right? Sometimes the chemicals listed on the ingredients list might not look super familiar to you. But knowing how to interpret and take apart and figure out what's actually in those substances will help you better know what's going on in your life. And that is really important. So we're going to look today at these three parts. This is page 4 of your packet. Page 4. So we're going to look here first at the structure. Now I'm going to try and keep this quick because you have the instructions right here. Okay, we're literally going to walk step by step through these instructions and draw the example. Okay, so I'm not going to go into tons of detail here. So let's go ahead and take a look at the first one. So this is actually showing our transfer of electrons. It's kind of like what we saw in the last video, right, where we have the electrons starting on the valence electrons, like starting on the metal and then moving to the non-metal. But this is just going to more explicitly show that transfer process. And so we're going to be looking at the example of a compound made of magnesium and oxygen. Magnesium and oxygen. I'm going to zoom in a little bit more so we can see this. The instructions. There we go. Okay. So let's go ahead and take a look. The very first thing you're always going to do is draw the electron dot diagram, the Lewis dot diagram for each of the elements. So we're going to draw one for magnesium and oxygen. And I'm going to color code these because why wouldn't I? It helps us see our electrons better. Okay, so here we go, color-coded. Now, remember, to determine the number of dots that you place, this is the number of valence electrons the substance has. You can use its position on the periodic table to determine that. This has got to start getting to be second nature, right? We've done a lot of practice here. So remember, magnesium is in our second column on the periodic table, so you can count 1 for sodium, 2 for magnesium, 1, 2 dots. Oxygen is right here in the periodic table, so we can count from left to right, skipping the transition metals. 1, 2, skip the transition metals, 3, 4, 5, 6. So we draw 6 dots. Now remember, as we discussed before, right, technically it does not matter which side you start on, but you want to make sure that each side has a dot before you double up. So that is step 1 done. Check. All right, so next we're going to show arrows to show the transfer of electrons from our soon-to-be cation to our soon-to-be anion, i.e. our metal to our non-metal. So remember, we want to get buddies for each of our electrons here, right? I do kind of empty circles to show where those are going to go. So I'm going to draw from this electron on our magnesium to that empty spot, from this to that empty spot. So that right there, that is step 2. We know now where our electrons are going to be moving to. Step 3 is actually moving those electrons. So we can't physically pick up and move those dots, but we can clearly indicate that those electrons are no longer on the magnesium and have moved to the oxygen. And we can do that by crossing out the dots on magnesium. Right? So now magnesium does not have any valence electrons anymore, right? We've clearly crossed them out. They do not belong there. And they have been added to our oxygen. Now to just really send this point home, I'm going to color code those dots on our oxygen using the color orange, just like they were on magnesium. I did not mean to make them larger. That's just kind of how that happened. So that is step 3. Now you're going to keep moving electrons until the cation metal has no more electrons and the anion, non-metal, has a full octet. Now, we've already reached that state, right? Because our magnesium has lost both of its electrons, and our oxygen has gained both electrons it needs. Sometimes what's going to happen, though, is you're going to have situations where after one of your particles is full or empty, you still have more stuff to fill or remove, right? And that's when you need to add more of whatever you need to add more of. And we're going to go over a situation like that in a minute. Last step is you're going to give the charges of each element. You're going to write next to the element in the charge corner, which is the upper right corner in the exponent position, what the charge of that substance is. So magnesium lost 2 electrons. So it's going to have this charge size is 2, and we lost negative charges, right? And so that gives us a +2 charge. Now oxygen gained 2 electrons, right? And electrons are negatively charged, so it gets a -2 charge. That's it. That's that whole thing. It's pretty simple once you get a little practice in. The hardest part, honestly, is drawing the Lewis dot structures, right? It's a puzzle piece. Move them over. Let's go ahead and look at an example. We're going to do a second example with aluminum and fluorine. Okay, so aluminum has 3 valence electrons. And fluorine has 7. And you'll note, right, I drew my last one to the right that time instead of the left. It's just going to mean that I don't have to draw my arrows quite as long. I'm just trying to save myself a little bit. I really should have drawn, you know what, let's move this one over to the other side because I think it'll just mean fewer arrows or shorter arrows, and I'm always down with doing slightly less work to get the same result. You know? Sometimes you just got to make your life a little bit easier. Okay, so these are all nicely color-coded. So we're going to go through the same process with aluminum and fluorine. We drew our electron dot diagrams, check. We're now going to go draw arrows to show the transfer of electrons. Okay, fluorine only has 1 spot to fill, so there it is. Cool. We're now going to move that electron over. Cross it out on aluminum, draw it in on fluorine. Let's go ahead and check. Are we done? Fluorine has a full octet. 1, 2, 3, 4, 5, 6, 7, 8. So it's good. It has a -1 charge. Right? We don't need to write the 1, but I wrote it anyway. What about aluminum? Aluminum still has 2 valence electrons. And that isn't what it wants. It wants to get rid of all of them. So this is where step 5 comes into place. Okay? So you can add atoms of these elements if the electrons don't balance out. Check it, right? They don't balance out. This aluminum has 3 electrons to get rid of. Fluorine can only hold 1 of them. So that means we got to add more fluorine, right? If 1 fluorine doesn't hack it, you got to add another. And maybe another one after that. All right, so let's go ahead and draw in a second fluorine. Move another electron over. Add our charge. And we still have 1 more electron on aluminum. Now, you could be like, oh, well, I'm done here. I don't want to do it anymore. But you'd be wrong. That's not how it goes. We got to add 1 more fluorine. Now, sometimes when you're doing these, it's going to feel like it's going to go on forever. It's not. It's always going to end eventually. Just hang in there. Sometimes it's going to be a case where they don't match up well at all, right? Where you think, you're like, oh, my non-metal, I got to add another non-metal, but oh no, now I need to add another metal. Right? That's going to happen sometimes, and you just got to keep going, keep bearing with it. And when you're doing the practice, right, your symbol is kind of small, especially when you get to larger compounds. Okay, so here we go. Let's go ahead and double check. So our fluorine, now each of our fluorines, all 3 of them, have 8 valence electrons apiece, giving them each a -1 charge. Our aluminum has lost all 3 of its electrons, giving it a +3 charge. And so we're done. That's it. Now, clearly, this one took a whole lot longer than our first one and is a little bit more complicated. But ultimately, right, it's the exact same process. We just had to add more of one of these substances. Now, the cool thing about this is it helps us better understand where our chemical formulas come from. Magnesium and oxygen bond together in a 1-to-1 ratio, 1 cation to 1 anion. And that means that we can write its chemical formula as Mg, 1 cation to 1 anion. In aluminum and fluorine, we have 1 cation to 3 anions, 1 to 3, which means that our chemical formula for aluminum and fluorine is AlF3. Note that 3 is in a subscript position because that tells us amount, right? So we can see how we get that ratio. Next, we're going to look at a way to actually come up with this chemical formula without going through all of this rigmarole. And that is the crisscross method. So go on to the next section, we have the crisscross method. So on the side of this paper, what I want you to write is I want you to write how to find chemical formula. And draw a big arrow pointing down to this section here. Now we're doing that because I forgot to do a good header here. So we got to add that in. So this is how we're going to find the chemical formula in a much faster way than doing the electron transfer, showing the structure of how the bond is created. This just goes a whole lot faster. And so again, we're going to use magnesium and oxygen as our examples. Magnesium and oxygen. So we see step 1 here says write the ion notation with the charges above each element. And actually, let's space these out a little bit more because I just want to give us more room. Now remember, our ion notation, or our ion symbol, is our chemical formula plus the charge of the ion. We're in luck because we already figured out the charge. Magnesium is a +2 and oxygen is a -2. Now, next step, and actually let's go ahead and let's color code this, right, because this is just going to, having everything color coded is just going to make it way easier to see what's happening. So that's what we're going to do is we're going to cross out the plus and we're going to cross out the minus because this no longer is applicable, right? We need to know that they're opposite charges. That's important. That is what allows them to bond together, but we don't need that information anymore to figure out the chemical formula. Next is step 3. We're going to swap the numbers of each element and rewrite them as subscripts. Right? So I like to combine step 3 and 4 here because I don't like to switch them and then rewrite them. I like to just immediately rewrite them. Right? So we get Mg, right? And that 2 has moved down to the subscript position. Remember that 2 came from the oxygen. We're going to go over another example so we can see this more clearly. And O, right, we have our oxygen, and that 2 came down to join it. Right, and remember that 2 came from our magnesium. Now it seems kind of silly to do this when these are clearly equal and opposite, so therefore it will be a 1-to-1 ratio, but bear with me. What we're going to do now is we're going to reduce to the simplest whole number ratio. So remember, we can think about this as a ratio, as 2 to 2, or even 2 over 2. Remember, fractions are ratios as well. And when you have the same number, right, that means that for every 2 oxygens, every 2 magnesiums, you have 2 oxygens, right? That's the same thing as saying for every 3 magnesiums, you have 3 oxygens, or every 1,000,000 magnesium, you have 1,000,000 oxygens, or for every 1 magnesium, you have 1 oxygen. So we're going to rewrite this as the smallest whole number ratio, right? And we are reducing here. So now we're going to write this as Mg1. And now the magnesium and oxygen are going to claim their subscripts here. But you never actually see this written like this, Mg1O1. And that is because in chemistry, we don't include things that are not necessary, right? We like to keep things as simple as we can, which is not very simple most of the time, but we're talking about very complex things, which does mean when we can simplify, we're gonna simplify. So we will rewrite this as MgO because we do not include the ones. We don't include the ones, right? If we don't, because it's not necessary to include. It's repetitive, right? It's like saying, right, why would it even be there? We don't have any fluorine in this molecule, and therefore you don't write F0, right? You don't do that. There's no like carbon in this. We don't write C0, right? You just don't write it. And so the 1 is just kind of repetitive, right? We already know we have at least one of them because it's in the formula. So you don't need to write the ones. So remove your ones, right? All right, so we can see that this process is a whole hell of a lot faster, mostly, than the process we saw earlier. Now we're going to look at another example here quickly, and we're just going to look, and I'm just going to write it kind of smaller off to the side, and we're going to look at it for aluminum and fluorine, just so we see an alternate example. Right, so for our aluminum and fluorine, we have Al plus 3. We already know that from earlier, but also we can figure that out based on its position on the periodic table, or our cheat sheet notes on page 3, and F minus 1. I'm going to include the 1 in there just because normally we would just write F minus, but I'm going to include the 1 since we are needing the numbers here. We then cross out the charges and switch the numbers. And rewrite Al1, F3. Hopefully this is starting to look a little familiar to you. We can't reduce this, right? Because 1/3, 1 to 3, they don't have any other common divisor besides the number 1. So we can't actually reduce this any farther. So then we can just rewrite this without the ones, Al, F3. And that is exactly what we came up with earlier, right? By looking at these ratios of cation to anions, we came up with this. And it's the same thing when you use the crisscross method, right? Because our ionic compounds, they usually form larger crystalline structures. So we want to think about the ratio of cation to anion in the substance and not all of the cations versus all of the anions in the substance. When we start talking about covalent compounds, we do actually need to consider each and every atom that is in that structure because they are molecules. They exist in a very different way than our ionic compounds do. So we are looking strictly at the ratio. All right, so last part is how to name them, and this is super easy. This is the easiest part. Okay, so we're going to start off with magnesium and oxygen here. So the very first thing that we're going to do when we name them, and I know we're going pretty fast through this, you need to pause, if you need to rewind, totally do it. Look at it again, watch it later. It's on Google Classroom, watch it later. But yeah, I know we're going pretty fast, so I want to make sure that we get through all of it in one go. So last, but we're going to learn how to name ionic compounds. So remember, naming is super important because that's a large way that scientists communicate about these compounds, right? Through our chemical formula and through the names. And in your daily life, you are most likely to see the ionic compound name, like when you're looking at the back of a package of something, right? You'll see the different compounds that this thing includes, and you'll be able to better make sense of it. So the first thing that you're doing in the name is writing down the substances involved. So we have magnesium. Ooh, let's write the full name. magnesium, and oxygen. And again, I'm going to color code this so we can see this more clearly. I think we probably get the picture by now, but still. Makes your notes prettier too. And pretty notes means that you're more likely to look at it. All right, so next, so we just have to figure out, first you got to figure out what the heck is even in this thing, right? What are the elements involved? We have magnesium and oxygen. One thing I want to point out, right, is that each and every time we're looking at this, we are listing the cation first, the metal first. And that is how it always goes. You never list the anion first. It's always the metal. It's always the metal, always the metal. The metal is first. You can remember that by like the metals are to the left on the periodic table. They come like before the nonmetals, right? Or I just memorize it. It's cation first and then anion. Or metal then nonmetal. That is also alphabetical, isn't it? Yeah, it is. So alphabetical order in terms of type of element, not in terms of element name. Okay, so let's go ahead and take a look here. So when we're writing the actual name, the first thing we list is the cation. Now remember, these are in ratios, right? And most atoms, most elements have like one charge of ion that they form. So just by knowing the name, that will tell you what these ratios are. You don't need to account for the amount of that substance in the compound. You do for covalent, but not for ionic. So now we're on step 2. We're going to name the cation. So the cation's name is magnesium. I know when you say, ooh, name the thing, right? Maybe you want to come up with a fun name for it. But no, we're not doing that. We're writing down its element name, right? So we have magnesium. And next we're going to write down the anion name, except with one change. And that is, instead of writing the full name of the anion, we actually change the ending to IDE. So instead of writing oxygen, we write plus IDE, we write oxide. And I know that this seems a little silly, but it's actually super, super, super helpful. The endings of compounds actually tell you a lot about the structure. In this case, the ending oxide tells us that it is a compound that has oxygen in it. Right? There are other endings that we use for very specific circumstances, but almost all compounds, organic or, ionic or covalent, there's also another class of compounds called inorganic versus organic, but that's like a whole nother thing that has to do with the types of elements involved, not the type of bond. And it also has to do with the type of bond. But, right, so this ending IDE, this tells us that this is not just two elements. These are two elements bonded together. And so that's what that IDE meaning, ending means. Now, all nonmetals, right, in the ionic compound will end with this IDE, right? So oxygen becomes oxide. Nitrogen becomes nitride. Sulfur becomes sulfide, right? Now, the other ones are a little bit easier, right? Like fluorine. Fluorine becomes fluoride. So if you've ever been to the dentist and gotten a fluoride treatment on your teeth, fluorine becomes fluoride, right? That is, you got a treatment of fluorine in its ion form, not in its atom form. It was in an ion. Right? That means chlorine is chloride. Phosphate. Phosphorus is also a tricky one. So let's write that one down too. Phosphorus becomes phosphide. Right? All right, so that is how we draw the the structure of an ionic bond, right? The electron transfer from our cation to our anion. That was the first thing we did. Next, we learned how to use the crisscross method to determine our chemical formula. Remember, chemical formula is very important. They tell you a lot about the compound. You also could determine that using the structure showing the transfer of electrons, right? It is just way faster to use the crisscross method. And last, we learned how to name ionic compounds. And that also is really helpful because, again, it helps you communicate about these materials. Also, that's mostly how you're going to see them represented in your daily life. You'll see them written as the name rather than just the chemical formula. All right, hopefully you all got all of that for your notes and are ready to do some practice.